very much for having me. It was a pleasure to be in the Friday seminar. As usual, this will be very informal actually. So I will run some code for you. So we're doing some calculations live. It will be some really easy code, so don't worry. So you shouldn't expect to be on notice level after this lecture, but hopefully I can give you some reason to look into kind of doing those calculations yourself, because it's kind of really excitingly helpful, and a lot of good results in fields you like, even in fields you don't like, have been obtained kind of by computer experiment. So the first half of my talk is really we just do everything we like, kind of I always explain what I'm trying to do, and then we do it in mathematical or macro, nice for you, and we kind of solve the problem. And eventually, for the last problem, I hope I haven't tested that. I hope to do some really live calculation where I don't know the answer, and we'll see what comes out. And maybe roughly in the second half, I go into some details of the field itself. So what the field is all about, so the first part is experiment, and second part is what the field is all about. And yeah, we'll see how it turns out. But for now, let's just get started. So if you can't solve this equation, that's probably not your talk. But essentially, the whole point of computer algebra is to solve some form of an equation, whatever equation it is. It can mean any of those. It can mean something really sophisticated. You can solve equation mechanics. So I really, when I started off, I really never believed how powerful that is. I always thought like I'm doing some abstract mathematics nonsense. So there's just no way that this would be useful for what I'm doing. But I have several papers by now where I just use a lot of. Sorry? Okay. Where I just use a lot of those tools. And for example, if you are a candidate, I know that plenty of people are candidates. The one at the camera right now. So you can easily feed a computer die. The system, I had one that was spanning 2 pages, and I was just too lazy to crash. What happened?
It has to go this way.
I was hoping I get a picture of myself.
But they
it should be good.
They can't see the screen at all. Besides.
Oh, I'm not sharing screen. I see. No, it should be much better.
Okay.
Okay. Sorry for not showing screen. Anyway, so you can solve all of these equations in various forms of calculus, or algebra, or groups, or polynomials, or multiplication, or whatever you want. And what I would really like to stress, because I got that wrong like a million times. So this is not kind of numerical analysis, it could be some field that solves things approximately, but computer algebra wants exact solutions. So what you actually can do, and I did that several times, you have some equation, some counting problem that you just way too lazy to do yourself. So you just ask your favorite computer algebra system to solve it, and just put that in your paper, and that's totally fine because the exact solution is probably even better than me doing it myself. Because I'm really not a computer, like Jolene said yesterday. Some people are really good at computing. I'm certainly not very good at computing. I'm really bad at computations. It's usually a much better idea to just fit it in some algebra system and just say, okay, that's what you need to do, and whatever. Mathematica will tell you that the number you're trying to count here is 1,012,000. That's perfectly fine. So all of these are exact calculations. That's kind of the whole point. So you could really just do it. In some sense, you can just do it and put it in your paper. So this is kind of the difference between those. And I really would like to start with 3 examples which we do like. One of them is chemistry, because chemistry, who doesn't like chemistry? So really fabulous example how computer algebra can be used in various fields. And then I have representation theory for you, which is some very easy representation theory that you can follow even if you don't know what representation is. So this is kind of a question about the molecule you see here. So we have 6 atoms of carbon, like around a kind of circle, and then some H points on the other side. And yeah, so we'll do that live. And there was this old question, we'll see a nice answer. There's some conjecture a long time ago. I'm not quite sure how they came up with this conjecture that long ago, but essentially it's about how many configurations you can have. Right? I just saw you a planar picture, but this is somehow limited in free space. We can take various forms, various ways how it embeds in free space. And Zach conjectured that there should be a continuum of those possible embeddings. And way later, using Mathematica, I'm just copying the paper essentially, or that talk. This was kind of really beautifully addressed. And I'm going to show you how that actually works. Right? So you kind of want to understand how this molecule is possible to sit in space. So the whole steps we will do is we kind of create a model. Then we try to solve the model, and this is where usually some form of computer algebra might enter the game. And then there is a step of interpreting the solution. And all those things are kind of interlaced and crucial. So very often it happens that you have a model, you solve it, but the solutions that don't tell you anything, then you kind of need to redo it from start. So this is one of those examples where there many people tried, had different models, and the solutions were always like a little bit like, yeah, okay, you solve the linear equation in 18 variables and you get some result that doesn't really tell you anything. But the solution I'm going to show you is actually pretty nice. And we do that in about 5 minutes live. But let me kind of explain what will come out. So there are supposed to be 2 different configurations, which I'm going to give around in a second. So if I would be a real human being, not just a simulation of one, I would have gotten them much bigger. But this is what I got from a hardware store. So I can give them around already. One of them is a chair, and you can try to wiggle it. It's very stiff, you can't move it. And this one is very flexible. You can try to move it. This one is called the boat. Right, one of them
is this benzene?
Excuse me?
Is this benzene? Is it chemical benzene?
Yeah, exactly. This is a boat.
I thought the guy who first conjectured that was Kepler.
Oh yeah, fair enough. This is kind of the general version, not just for 6 bonds, but with any bonds in general.
All right. I see.
So I'm a little bit cheating. I'm only doing the 6 bond version because it kind of runs faster.
Yeah.
But yes, it's exactly that. That's the chemistry. And you have those 2 types of solutions, which I don't know why people call chair and boat. Maybe you can see why they're called chair and boat. For me, neither of them looks like a chair nor a boat. But anyway, you have those 2 of them, and they're really incongruent. You can just see that. And the chair appears just really often. And the boat is just really rare. But the boat kind of, there are many boats. So if you had it in your hand already, you can kind of twist the boat. So there are many solutions for the boat, while the chair is essentially, it doesn't move. It is what it is, right? So yes, and that's what kind of was conjectured. There's this continuum of solutions for the boat, and you have this kind of fixed solution given by the chair. And kind of people, as I said, people try to do that, and they get that back and forth because it kind of really depends. It looks always very simple from some point of view of some outsider like me, how that actually works. Because you see a model that's given by someone, and someone solved it, and the solution makes sense. But usually there's a lot of trial and error involved. People sometimes need to go back and come up with a completely different model. And that's exactly what happened here. So there are many solutions between those two times here. And I just show you kind of the most beautiful one, in my opinion, which explains this continuous movement actually very nicely. Okay, and don't look too much at the equations. We'll do that in Mathematica in a second. But essentially, I think of those bonds as being variables, A1, A2, A3, up to A6. Or in general, come back to your question, you can do that for all n. So there's heptane. Heptane would be the one with 7 carbonides, and there's octane, would be the one with 8. So on, but I'm just doing the 6th one here. And these are the equations you course, the star is just the dot product of the angle between them if you want. And it turns out that the angle should be 109 degrees. So if you would take the arc cosh of 1/3, we would get 109 degrees, which I must apologize now, I don't know where the model is, but if you go to a hardware store, then there's no way you get angles of 110 degrees. So all of these are actually 90-degree angles. But essentially nothing I can do. So like I wanted a 10-degree angle. Anyway, it still works out pretty well. Anyway, so you can have those equations and 6 variables. And the last one is kind of, the first one is the length. We fix the length we want. That's the normalization. The second one is a really crucial one, the angle between them. And the third one is the simplicity coefficient. Like you could see it in the picture. And what I will do in a second, I will replace those guys by variables, and I will have polynomial equations that I need to solve. So I replace them by variables. So we'll do that in 1 minute. And then the solutions will be given by intersection of varieties. And what this paper actually proposed is how can you compute those intersection of varieties? Well, you can use something that is really, really popular in computer algebra, and that's theory of recurrences. So recurrences, you kind of see them like in a second, are kind of built such that you can solve polynomial equations with many variables. It's really, really cool. So whenever you have polynomial equations with many variables, you should look up recurrences, and you should use computer algebra to solve, or at least get a hint how to solve your problem. So we'll do that in a second. Okay, I show you the solution already. So it will turn out that the intersection of all of the polynomials is a circle, and this is where all the bones live. And then there's one isolated point, and that's where the chair is. And we do that in a second. So that's what I originally wanted to build. That I stole it from the paper, which is way better than my version. I apologize again. And just a simulation of a human being. I should have done those. But even though these guys weren't able to get 110-degree angles, it's still 90 degrees. Anyway, so that's what you have in your hand. This is just much bigger. So the left one is the one that doesn't move, and the right one is the one where the solution is actually like a continuous solution living on the circle up here. Really nice. Okay, so let's do that live now. So let me pull up. You see where my screen is. We need to go left or right. I need to go left. Oh. So I did this in Mathematica, and it's very, very simple. The code is extremely simple. We'll do that step by step. Essentially, there is already a built-in command you can use. So really, if you hit this problem, it's a matter of if you know what to do. Obviously, now I know what to do. But usually, it's a matter of an hour. Instead of trying to do it by hand, which might take you, if you do the heptane version or the octane version or the dodecahedral version or whatever, higher ends will take you just a very long time to do that by hand. It's very, very simple. I don't expect you to really understand the code, but it's somewhat self-explaining. So I'm skipping the first step in the paper. So they explain that the whole system of solutions will boil down to this matrix, which I just feed it into Mathematica. I can make it a bit bigger. Give me a second. So the matrix here. So my variables are x, y, and z. So let me briefly go back to my slides if I can find them. So it turns out that you have all of these. So you have quite a few of them, but you only need 3 of them, which are my x, y, z variables. I have that somewhere actually, but anyway, let's forget it. You only need 3 of them. Let me just write it down. The first step is that they show that S13, S3, 5 is counting the next step, S51. If you know those, you know what the other is. That's why I have only 3 variables, and I call them X, Y, and Z. Okay. The first part is really just, and I kind of skipped that. That's not super interesting. Just do some linear algebra and convince yourself that the equations I wrote down before are equivalent to 6 subdeterminants of this matrix. subdeterminant of this matrix, which I will show you in a second, which are obviously just polynomials in x, y, and z. So you have 6 polynomials in x, y, and z, and the solution space is the intersection of all of them. That's kind of the first 2 pages of that paper. Let me just set up everything. So first I just set it up, and here's one of the subdeterminants. As we would take, for example, the subdeterminant of this matrix, which is just now the top left corner. And you don't want to do that by hand. You can just ask Mathematica to do it. And I just did that, and here are the polynomials. Okay, so right now we can't see anything. We just have a bunch of polynomials. And yeah, what to do with those polynomials? So people got stuck on exactly that problem here. So you have a bunch of polynomials, and they look pretty random to me, except that they're in x, y, and z. You can have everything like x, y squared. You have a xz squared, x squared, z squared. You probably have an xyz somewhere. It's a big mess. Right? So it's a huge big mess.
Just like not simplified, or just get out of like term of the same.
Oh, you like it? So, yeah.
Oh, is it also not simplified? Like, or there's like.
Oh, I can simplify it, but I won't have. I will simplify it in a second. But right now, for the one that you is the determinant without anything to get. So ask me to get, and I can't say that. So I would like to simplify it. I could just do the following. And we'll see what Mathematica says. Okay. Well, it's still pretty much a mess, I guess. Okay. But if you run this magic command Ripner basis, it gets much better. First of all, it reduces the system. So it detects automatically that you have 6 polynomials, but you only need 4. That's already great. And the polynomials are much easier. For example, the first one is completely free of any z's. Just an equation in x and y. The last one is just an equation in x and y as well. Very good. And the middle ones are just linear in z, as you can see. There's no higher power of z. And this kind of happened because I said z is the variable I really dislike. So this order is just, I dislike z, I kind of like y, and I really like x. So the polynomials are arranged in a smart way such that the kind of z is kicked out as much as possible, and you can kind of really see that. And if you'd like to do that now, so now they factor much better. We'll see that in a second. So the first, the factorization up here, the simplification was just not really nice. And here, so the first one is irreducible. So I can't do anything with it. The third one is irreducible, and the fourth one is irreducible as well. There's nothing I can do, but the second one clearly splits into 3 parts. And as you can see, the first 2 factors are really, really simple, and those factors will give us a chair in a second. And then there is this larger factor up here. So what I can do is I can run the same, but just split the basis now as follows. I can't do anything with 1, 3, and 4, so I just put them here, 1, 3, and 4, and I split the last one into factors, and I do it again. And now you see really easy polynomials here. You can solve this by hand, right? You are looking for the common zeros of the space, x plus 3, so x divided 3. And you can solve for y. As soon as you have y, you can solve for z. It's pretty simple now, right? Compared to what it was before, which is just this horrible mess of variables. We can now do this by hand. Same here. Really, really simple. X is, what is it? -1/3 or something. You can solve for y, and you can solve for z. Then you can do it by hand. Obviously, I will not do it by hand. I will just do it right here for you. And you will see, I will run that. The first one has just 3 solutions. The second one has just 3 solutions, and the last one, oh, sorry, I'm not solving the last one right now. The first one has just 3 solutions. The second one has just 3 solutions. So these are isolated points now in your picture. But you can somehow observe that only 2 will survive. by just saying that Z3 is actually solved by some of them. So I'm just saying substitute one of the solutions, this one here, into the Z3, and I get 0, 0, 0. So the second one is actually also a solution of Z3. And if you run that, only 2 will survive, which is exactly the chair. So this one will survive, and this one will survive. Here's our 1/3. That's exactly the angle for the chair. It's a 110 degrees. The other one is a bit strange because that's the following problem. So what angle does give you -3? They're just imaginary solutions. But sometimes happens, all of you know that I've seen that before, that you get a solution like this, and you're actually only interested in one solution. You only care about x equals 1, and the other one doesn't make sense in the real world, and it's the same here. So this solution has an imaginary angle, doesn't really show up. And the only one that survives is a particular isolated point at -1/3, -1/3, -1/3, which is exactly the 109 degree angle for the chair, which is somewhere in yours. And if you do the other one, I just did that. So the remaining equation is U3, and you run it, you get this intersection of those two algebraic varieties. And as you can see, the intersection here is exactly our, I can try to make it a bit bigger. The intersection here is exactly, no, it's kind of running really, really slowly. Let me try to make it a bit smaller. It's exactly the little curve, the little circle that lies tilted in space. Maybe this is a good picture. The intersection here is the circle that lies tilted in space. And that's exactly what the paper does. So you get this one solution that is completely isolated. -1/3, -1/3. Which is our chair. And you get this intersection of those two varieties, which is kind of the circle. You'll see the second again, the likelihood to fill the space. Which is, well, the bonus. And the bonus is a continuous solution. I have had it in the hand there, moves continuously, and all of these configurations will live on this stuff.
Where did you see the -1/3? So where is that point in your picture?
Oh, and then one shot, it's just a singular point mathematical one display that. Sorry, this is the third solution, it doesn't appear on this solution. I put the solution on the part.
Okay.
Okay. Yeah, here again, the boat, right? So the tilted circle. Let me pull up this one again. I hope that's kind of visible. The tilted circle here in space. And I think that's an absolutely fabulous solution. No problem. So all boat solutions rely on this curve, and you can calculate the angles you want. So you ask for the 300. Do that, and then you have this isolated point at living at the chair. And all of this was doing, it's a pretty brilliant idea, is it was really, really a simple calculation in the end. It was just feeding in a problem which looks kind of impossible to do by hand into some really simple algebra that was already existed in mathematical, which is run it and you get a quite a beautiful solution. So I think this is a really beautiful example of how experimenting with computer algebra can really help you in practice. Right? So now we imagine that in chemistry and we'll do something similar. Okay, I will now go to a representation theory example. So any questions on chemistry, which I try to answer. Awesome. And this is, of course, just kind of the tip of the iceberg. Took this one because I really liked it. See.
Maybe just a comment about derivative. I remember this comment from Math Overflow that somehow derivative bases are just linear algebra, but your complexity goes from like, if you think about linear algebra, it scales, the complexity kind of scales with the dimension. And then in Grosvenor basis, for whatever reason, the complexity scales in the cube of the dimension. And so it's like, if you have a Grosvenor basis problem, you can expect to solve it when it's reasonably small, but you can very easily blow up any computer algebra system with a pretty easy problem.
I will say something about that in a second. Yeah. Yeah. So for small problems, it's actually the Grosvenor bases are extremely good, but calculating them is extremely difficult. Say something about that in a second. Okay, let me skip this. Before I can say something about this, just the notation. So as this famous notation, people know as big O. It's actually an omicron, but you can't say the old omicron before. So somehow it got stuck as big O notation, and it's just the following idea. You kind of want to have some long-term behavior through algorithm, and you can kind of stack it here at it's in big O of G in this picture, which is just saying that there's some constant, no control over the constant, such that eventually, from some point on, I have no control, my f will be below that point. And what people then usually do is that an algorithm, then they want to know kind of the worst case scenario, not the average case scenario, but the worst case. Okay. And the worst case scenario of Grosvenor basis turns out to be really bad. That's kind of, I think, what Jordi said. So the worst case scenario for Grosvenor basis, I plotted that down here, is D is the maximum degree you see in the polynomial, N is the number of variables. And it's polynomial in D to the 2 to the N. Yeah, so you will very, very soon kind of run out of well, computer power, which is really sad because Grosvenor bases are extremely strong, but somehow you need to pay a price, and here's the price. It's really difficult to compute. And in case you don't really have a feeling about the growth of this function, it's a green one in my picture, which in a log plot, so log plot means I scale the, I will comment why you can't see any numbers in a second. I scale the y-axis using a log. So when I go up 10 steps on X, I just go up 1 step on Y. 100 steps on X, 10 steps on Y. And in this log plot, the one of these functions, the one that grows like the Grosvenor algorithm, just outruns my other example, like a lot, right? So here you have 2 to the N in this plot, because this function grows so fast, looks like a line. Right? So that's how fast this function actually grows. And I got really confused why I don't see any output here on the y-axis, but if you check the numbers that I used here, I only got 25. There's hundreds of millions of digits. So in Mathematica, just immediately subtract them. So the number 2 to the 2 to the N has something like 100 million digits or right. Which is somehow I said again, it's kind of a price you need to pay. This is absolutely fabulous, and it definitely will help you eventually in your research. I used that already several times, but maybe not for bigger problems, just because the growth rate is really bad. And the whole gist of the field is somehow to find kind of smart algorithms which do a little bit better. Be better than this one, it's pretty easy, I guess, but they are not as bad, right? So you would like to run them much further than just, I don't know, if N is 10 and D is 5, then it's probably already too far away.
That's a question.
Oh, yeah.
I think these worst case scenarios and doing something exceptional, or should I think of these worst case scenarios as being something exceptional, or is it relatively common that it just explodes?
That's a really good question. That depends on the algorithm. For Grosvenor basis, it's relatively common. So this is essentially the average state as well. But for many algorithms, the worst case is much worse than the average state. Really good question. So people usually study the worst case, but for practical implementation, the average case is somehow more.
And is this characteristic dependent? Does it have to do with characteristic?
Characteristic.
Oh, it is.
Oh, this is completely dependent. in one of the metrics here, so it's really just linear algebra. So really smart linear algebra, which is discovered in the 60s, which was pretty late. Oh, fun story here. Everything here is due to actually to Buchberger, and Buchberger named everything after the advisor from Gröbner, and now everybody somehow forgot about Buchberger. So if you're writing your thesis eventually, be careful how you call things. Okay. So it's also this one. It should be Buchberger basis, but Buchberger decided to call it the Gröbner basis. That's just what it is.
And then maybe just a comment is that, if you think about a polynomial ring, and look at its homogeneous components. And so if you have, let's say, n variables in degree d, the size of that space is the number of monomials in d variables of degree d. So in n variables of degree d, which is like n choose 2 with 2 brackets. And so somehow, like, as you go up, the vector space dimension is increasing enormously. And that's essentially where the complexity comes from. You're trying to do things in a very, very large dimensional vector space. That's essentially linear algebra, but in very big spaces. And like we know, linear algebra, becomes complicated when the space is, big dimensional.
Right. So linear algebra can still be very complicated and with respect to that.
Okay, let me check the time.
And maybe just the practical thing with Gröbner bases is that it's very easy to decide. So I've often had a problem where I expect magma to do very poorly. So I should also say that magma is actually the winner in Gröbner base, like of all the computer algebra systems. And sometimes so my ability to estimate how difficult Gröbner basis things are going to be is very poor. But you can do it very easily just by plugging into magma, hitting enter, and then giving up after an hour. And sometimes I had one thing where I had this thing in 60 variables or something, which I really expected it to do horribly on. I hit enter and it gave me the answer in like 2 minutes. And so it's worth trying sometimes with me luck.
Right. There's a lot of trying, exactly like a square model. Sometimes you need to have a different approach. Just give up on an express approach altogether. But again, it's a super power. It's just extremely good.
So let me maybe jump to the third problem I had, because I can still do that before the break, and then we come back to the second problem. So this is really this is a picture of my life, if you want. I'm always in this try and fail circle, but maybe eventually you come back to success. And I will try to, my 2 examples here, representation theory. I will try to tell you that it could also be failure and it could be success. It really kind of depends. You should try, because otherwise you will never get out of this little try and fail loop, which is my whole life. So let me skip this one first, and let me come back to it in a second.
I want to do character tables. So if you are attending Jodie's seminar, Jodie and Chris's seminar, will be very familiar with character tables. So here's a character table of a very famous group, the Mathieu group 11. If you don't know what that is, it doesn't matter. I'm going to do a much simpler character table in a second. But the character table is a nice picture there, which I got out of Mac. You'll see that in a second, like again, which is really just a square matrix in the irreducible characters on the left, and the conjugation clauses of the group on the top. So the conjugation clauses here are named 1 to 10. Magma tells you the sizes as well, and it will be important in a second. If you like modular representation theory, Magma will tell you the order, so the primes may be capital. And as you can see, there's 2, 3, 5, 11. But the main point for me is exactly this little block here, which I call the character matrix. So in the first, column, you see the dimensions. That's the column of the class, the class of the unit, which is always of type 1 dimension. We have 1 dimensional, 10 dimensional, whatever, 55 dimensional, and the rest are the traces of the matrices on that character. And there's a famous theorem, which you can find, for example, in Bernstein's book, that every bigger than 1D simple character has zeros in its column, in its row. and I mark them for you in color. In every row, except the first one, the first one are the linear character, the one-dimensional characters, and one-dimensional characters cannot have trace 0. Group elements are invertible, so they can't act as 0 vertex. But if you have a bigger matrix, you can easily have an invertible matrix trace 0. Have zeros in the corresponding rows of the character table. And first that tells you that there's at least one for the bigger one. I just mark. And another question that arises immediately from this picture is kind of to determine where the zeros are. And as you can already see, there are a lot of zeros. Like they're quite few. And that's kind of
the reason for that. So what's the reason that every single character has a 0? No.
yeah.
Like, what is the reason for that statement? We'll go to that statement.
Oh, I don't know. I haven't put the proof, but this is kind of very fast for me. I don't think it's completely true. Okay. I haven't looked up the proof. I'm not well prepared, as you can see. But my point is that let's believe this. So that it is 1, 0, and I would like to count the numbers. The numbers are 1. I would like to count the numbers. The right ones are 3, the green ones are 2, the pinkish ones are 2, and then 3, 5, 5. Okay. You get the point. Count the number of zeros in those character tables. And I will do that for you live in a second. And we will get some very strange pattern, which you can. We will feed the question into Magma in a second. And Magma will essentially tell you the answer. Of course, you still need to prove it, but it will be quite clear what the answer is to the question which I'm going to formulate on the next slide. Okay, so here's a much smaller character table. S4 has 2 one-dimensional characters. I'm ignoring those, I'm in 0. So ignore those. They won't play a role anyway. And ignore those. And we are looking for the zeros. And I'm asking the following question. What is the second one is a bit easier? What is the probability that the conjugacy class is a 0? Let's just say I take the matrix and I ask the matrix, that's the matrix itself, and I ask how many entries are 0. I have 5 by 5 matrix, I have 25 entries, and I see 4 zeros. So the probability of seeing zeros is about 16%. Now the question makes sense. I'm looking for the number of zeros in my matrix. So 5 by 5 matrix, I see 4 zeros. The probability is about 16%. A bit more sophisticated, I could ask the question, what is the probability that a specific element has character 0? Let's just say I weight every entry by the size of the corresponding class. In this case, I get 120. Why do I get 120? Because I have 5 characters and I have 24 elements. And if I haven't messed up the count, then this one, there are 6, and twice 8, that's 24. So that's 24 out of 120 elements act by 0. So two very similar looking questions, slightly different. I take the matrix out for the zeros, that's the P of chi, or I take the matrix and weight it by the group, by the number of elements, and ask for the number of zeros. And this is one of the problems that you really can't determine that in any easy way. But, well, we'll do that now in Magma. So let me just start Magma. So let's have local packages. The Magma is absolutely fabulous and was and it's still developed here at University of Sydney. So, and you can easily run it. So if you're very lazy like me, you don't even need to install it. It has an online calculator. So again, you can save a lot of time. Okay, I would like to ask the following question. What is the probability of pi as n goes to infinity, n very large or very large magnitude. So we go to that calculated by what is the probability that the element x is 0 or very large? And that's exactly the question the background like. We like it a lot. Because it has character tables, it knows how to compute character tables. I just need to ask for the percentages. So let's do that live. Let me just find my code. Give me a second. Okay. Yeah, oh, here we go. It's a very, very simple code. Okay. So ignore the first line. We'll come back to that in a second. I set up the real numbers with precision 10. So you'll see the digits up to 0 up to 10 digits. All right, I run to S7 because it runs very fast. We'll do that. We're going to run that much further. I take the symmetric group on those elements. I let magma construct its character table, and I would like to increase the count, which is exactly the count. And I just ask whether the character element is 0, and I just let me give it a count in the end. That says it. The size of the character table squared because it's a square matrix. Very, very simple. Nothing fancy. And we will get some beautiful mathematics out of this, whatever it is, 10-line code. Okay. So I'm not very impressive so far. This is 16 between before. So S1 has only one-dimensional representation, so that's 0. S2 has only one-dimensional representation, 0. F3 is the first interesting one. If you remember the character table of F3, let me see what I can remember that one. It should be something like 1, 1, 1, 1 minus 1, 1, 2, 0, 1. That 1, 0 is a 9 by 9 matrix, so the probability should be around that. Very, very nice. So let's go much further. I'm not sure, let's say something like S14. So S14 is so large that if I would put it on screen, you wouldn't be able to see much anymore. It's the character table. I checked it before. So now it's about 40%. Oh, very interesting. Okay, it goes up and up and up. I will have a nice diagram for you in a second. Just remember that this one, it's not quite clear what's going on here. So it grows a little bit at the beginning, and then around 30–40%, it kind of doesn't know what it wants to do. It kind of seems to converge some number around 35, 6, 7, 8-ish. Okay, so that's failure, because I could push it a little bit further, but I don't want to bore you by staring at the picture, which is the calculation takes quite a while. I push that a bit further, and the pattern won't really change. So let's say that you can't really tell what's going on. It somewhat wants to converge to a number between around 0.4, about 40%. Can't really tell. That was my this is square problem, the chi, and we don't know. I can't tell in this calculation what's going on. Spoiler, the other one will be a nice result. That could happen. It absolutely can happen to you that you run it and you can't tell it. But note here that you never do the calculation like this by hand, right? S14 has 14 factorial elements, and the whole calculation only took 2.8 seconds. That was not so bad.
14 factorial in 87 billion. So 14 factorial is around 87 billion.
Possible.
Like it's just, I just find it so amazing how.
Yes, it's really amazing. And actually, it's even worse. So if you want to, comment on that later. If you want to push the calculations further, you kind of need to be really careful, because what really makes it slow is that the characters get very big. The characters itself get very big, and then you have just this huge array of tremendous numbers, and that's just too much for the machine usually. But you can somehow cheat. You can just do a modular calculation. You only care whether it's 0. Anyway, so in this simple code, I don't do that, and it still goes in 3 seconds, and 14 factorial was already a very large number there. It's really exciting. So let me just do the other one. So this was this one, and we had failure. I can do this one. Right, rapid. Okay, here it is. It's not very different. Well, exactly the same, but I wait to count by the number of components, the differential difference. Let's see. Calculation. Oh, sorry, let me just go up to 14 immediately. That calculation will take about 3 seconds again. 2.7. Ah, this one is much more interesting. It started in the same way, of course. And the pattern is 60, 23, 25, 25, 27, 26, 50, 53, 55, 60, 61, 65. If you push that to S38, biggest one, I know what the calculator is around. Then the percentage will be around 0.99 something. It's pretty clear to get what the answer is supposed to be. The probability will go to 1 and yours. And as soon as you know that gap, it's actually not so terribly much. Okay, so what have we seen here? So my little code, which is really not terribly difficult, is like 15 lines or something. Right, you would run that maybe for 2 minutes instead of just 3 seconds, but you would see, you would immediately see that happen. Which is kind of a really interesting result that you just got from a little calculation in the group itself. I think that's actually pretty good. So
that's the probability that you get 0 on the character tensor for a particular element of group element.
this one?
Yeah, or the one you just read.
Sorry, the one is 1. The other one is, I don't know.
What was the probability that you found was converting to 1?
Oh, yeah, let me say that again. The probability that I find 0 in my graph table has a high probability. I don't know. It seems it's kind of bounces back and forth, even if you go to whatever 38 or whatever it was. The probability that a group element acts by 0, so a specific character, specific group element, that probability is 1. Essentially, all group elements have characters 0 on all group elements.
Okay. And so that's just grouping them not by quantitative class, but just looking at all the.
That's right. I really made it itself by the sign probability clause here.
You do the random element of the group and the random you're reducing.
And that's a better way of saying it. Take the random group element, pick a random character, that's a simple character, and the result will be 0.
What's random that it's converted to 1? It's very surprising.
So yeah,
It's quite surprising that
I think so. You get it from. I mean, the code took you 3 minutes to do, and even if you're a beginner, and you need now to write that code, maybe. It's really fantastic. Yeah, I have some time. So let me do something different here. So you can easily now change the code. Let me do that live. I don't know the result. I change the code, and that's a bit difficult because I need to look here. Yeah, I could ask is even instead of is 0. To do that, I probably need to do the following. Give me a second. Okay. Let me just run it. It probably will not run. Okay, so here's a problem you see very often. It will not run because it treats the character as an algebraic integer, although it is an integer. So the question is even doesn't make sense. So we'll just tell it to treat it as an integer. Give me a second. So what I will do is I set up the integers. Give me a second. And I just tell it that this actually is an integer now and that should work. Okay, very good. Ooh, I didn't do this before, but this is very surprising. So what I did, let me just tell you what I did. I asked exactly this question again. Take a random root element. What is the probability that the factor is even? And naively, we guessed 50%, and it turns out that this probably converges to 1 as well. If I run that further, this, I mean, look at the numbers, right? With the rows, and I only did up to S14. I didn't check that before. So if we would now run this to higher numbers, I claim this converges to 1 as well.
The 0 is even, so.
So actually, but not equal to 0.
Like 0 is an even number. And so you're just imposing.
Oh,
We get in.
okay, let me try something different.
And not 0.
That's a good point. That's a good point. Yes, very good. It's still a very surprising result if you don't know the other one. So that happens if we do calculated live. So let me try another one. Maybe we try something like how many are greater than 0? So GT is just strict radius line. See. I guess. Oh, I guess. Okay. Let me try again. That happens. Of course, it is also clear because we already know that it will be 0. So the number of ones that are bigger than 0 should go to 0. What I actually want is the other one where I don't know the answer. So let's see. Let's do it again. That happens if you do live. All right, let me do it again. All right, let's see the other one. So how many entries of the matrix itself? We don't know the answer to that one yet. Okay, so let's try whether we actually get something here. Come on. It's very good. So there's light error here. Try again. Oops. Right, this is now I don't know the answer, and I don't know the answer. The probability and an entry of the matrix itself. And it doesn't seem to go to 50%. Right now for S and P, the probability is about whatever. Right. This might go. Let me see how far I can do this. Maybe. Then we can take it away. Right, let it run. Let me just there you go. Okay. So what I claim now is probability and random entry of my matrix is even will probably go to 1 s equals because the sequence is increasing. It's not very fast increasing, but it clearly probably will not converge. But for 0, it was still a bit fuzzy. Okay, let me just summarize what we have seen here. So if you do that live, it's always a bit tricky. So Okay, so I put it to those in the graphs. So the probability of a random element acting as 0 is for S17 was the biggest one of the div. Alex did S38. Much smarter code, but anyway, 70%. The other one was the one we can't really tell. And that's my point. So you can really successfully solve one question. Essentially, you just need to do it now and just sit down and think about the proof. But it's certainly not going to be enough for the other. And what we did live, which took me way too long, and that's, I guess, the point of doing it live, is the probability of this one being even. And I had a graph that looked roughly like this one here on top. So I claim that probability of a random character entry of the character matrix 0 is even, also converges to 1. I think that's a good point forward. Thanks for not running away. Yeah, so we stopped here by experimenting. I have one more experiment, but I'm kind of low on time. So I'm postponing that, and we'll see whether we do that at the end. Because I also want to tell you roughly what it's done in the theory itself. And there's a beautiful idea that I'm going to sell. We do some calculations, well, live again. But there's really now an idea that I would like to sell, and it's really extremely amazing. And again, it's the same type of story. I never thought I would use that at all. And I eventually ended up using it, of course. And it's this idea of divide and conquer. So we have this problem with growth analysis where the runtime was astronomical, not going anywhere, not going anywhere for bigger D or bigger N. So a big part of the field is actually to find fast algorithms. To calculate character tables very fast or something like that. And I will just do a much more simple example for you than calculating character tables. I will just do multiplication for you. And the result is just ridiculous. So again, completely surprising. And yeah, let's just see how it looks like. It's really, really good. So the usual way I will start with polynomials, but we've got the numbers in a second. Polynomials are a bit easier to start. The usual way I will multiply polynomials. You all know multiply polynomials, but I will do it anyway. So you want to multiply that, so the left one, put them grid. So that's 4x minus 5. And compute all these entries. And multiply right down. So let's make a complexity analysis of this multiplication algorithm for polynomial. Well, because it's a grid, I claim we need n-squared multiplications. That hopefully is not very surprising. It's a grid, right? So you need n-squared multiplications. And you can check, well, let me just for this case. In this case, this n equals 2, and one addition. So the n-squared with 4 multiplications, 1, 2, 3, 4. And if you do the calculation, you'll see that you need n minus 1 squared additions. In this case, you need 1 addition. That's addition 1 the off diagonal. So in particular, let's piece them together. N squared, there's something with n squared again, and you forget about constant and polynomial multiplication is n squared, which is kind of expected. You just think of the grid picture. It's absolutely not clear why this should be possible to make it fast. And this is where this extremely great idea comes in. So let me just write it down again. What's called the story. N equals 2. We had 4 multiplications and 1 addition. And I will count subtraction and division as well. Don't worry about it. So 5 operations. That doesn't seem to be any smart way of doing it faster. But we can. It actually gets much faster. let me just do it for you once for n equals 2. It's a bit strange, I don't recommend doing that by hand. You can computer algebra, for computer, actually look. So that's an algorithm that can't super. It's pretty new in some sense. And it's set forward. So we still want to multiply those polynomials. So this is ax of b, the 2 by 2 case, and cx of b. And we do it in an absolutely complex way. So completely great. So completely great. So you multiply a, c, you multiply b, and c. That's going down my picture. A, C, B, but I said B. Very good. And you kind of need them anyway, you need them here. Okay. That's what we do. But then in order to get the middle coefficients, you kind of do something very strange. You compute and you extract the worst. You compute A plus B. And you compute C plus B. And you compute their product. So you have my additions. Another product. Okay? There are 3 products already, 2 additions, and then you subtract them. You do the subtraction of this term that you call u, and you compute u minus those guys. That's my it's fine. We'll put u minus this. And then these are together, you actually have computed so I have also one more addition that I can do. Again, we also have this one, a b plus bc, and then subtract u minus the. We have 4 additions, 3 here, 4, which compared to our 4 and 1, 4 really doesn't do a good job, right? Now we have 7 operations. This is kind of a very strange way of computing polynomials. So why on earth would you do that? With 7 operations instead of 5, and it's also not very intuitive. It's like the grid is somehow much easier, right? But actually it's not. And that's the whole point. That's the whole point of the strategy. Because in the end, you're multiplying, you're not adding. So this number actually doesn't matter. Somehow forget, you're telling the same value to forget. And then we have 3 here compared to 4. And that doesn't look like much. Like we take 1 operation, okay? But you can apply it across. So let me show you how that works. And you say 1 operation per each recursive call, which then grows exponentially. It's just an extremely fascinating idea. So here I just said again what we did. We have 3 multiplications and 4 additions. So 7 operations. But the point is we have 3 multiplications compared to 4 multiplications before. Right? 3 to 4. And what we do is now the following. So you divide the polynomial just for simplicity, that you do something to the power of 2, so we can kind of do that recursively. So you split the polynomials f into f1, x into 2, and f2, and g1, the other one will be by g1, x into 2, and g2. And these are now polynomials in more order, right? Half the degree. F is of some degree t, then f, for example, f1 will be 2 divides it very small. And then you kind of recursively do it on those guys, because it's just around the algorithm now 2 by 2 algorithm, which have 3 operations, 3 multiplications, and 2 additions. Additions don't really matter for those 4 polynomials. Here, our grid I think again 1, 2, 1, So doing the grid, I'm running a lot of so here, do this. 3 plus 4, okay. Then you have the first thing the same, the first thing the same, the first thing the same. And you will save operations. It's not really matter. Save operations. Here, I just did it. We end up with 23 versus 25 in the classroom. The case is just 25. 4 squared plus 4 minus 1 squared. And if you just do it for this 54 example, then you only need 23 operations. The point is, it kind of goes recursively. You know, call the same multiplication again. If you call the same multiplication again, you always save one step. I have a very nice calculation in a second. Although it doesn't look much, but it's just a little bit smaller than 4 because of this divided problem strategy. You divide the problem and apply the same recursive. You make a recursive call. You divide the problem, you apply the same strategy. But the problem, dividing into different pictures, one algorithm here, one algorithm here, but what the algorithm doing, taking the picture, divide it again, and runs the algorithm here, here. Okay? So divide and in this easy example, you do the following. So here's the illustration. Why is it so much faster? So my grid multiplication is just instead the area of the square. But now I say the multiplication per step, and ignore you the distance. But I draw this little square like this. I put it in itself because that's what I do. Next step, I have now 3 multiplications in one. All my multiplications are now like this. I put it in itself. I have a blank box over here, and now I have this level. Well, very much like on my slides. You put it in itself. 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 It just saves a ridiculous amount of complexity. We will go down to the fractal dimension of this picture, which is log 3. All my logs are base 2, which is roughly 1.9, 1.59. It is ridiculous. You just save one step, but because you call everything recursively, you save one step per step, and then it just gets this beautiful kind of fractal type picture. Really, really amazing. And it's then not hard to show then that the multiplication is just, you can just do it much faster. I will show you some comparison graphs in a second. And this is the much faster. So you go down to a problem which doesn't look like the ones to simplify, it's all a squared to something that is much, much smaller. Like this is log 3 word, all of n log 3. Is that optimal? Is that optimal? I will comment on that somewhere. Thank you very much for the question. But this is part clear what the fractal picture of in the and just think about the problem. We're multiplying polynomials. It's just happening everywhere, and this is just absolutely fantastic. Okay, I just compared them again. Below is the log plot now. Now log plot hopefully makes sense. I jump steps of 10. Then I just have a usual one on the x-axis. The top one is a regular plot, and it's just much faster than before. So for 100 steps, the top one needs 10,000, and the other one needs 1,800 or something ish steps. And again, this is polynomial multiplication. It's like happening all the time in your machine. So that's actually a really, really cool result. So some people, not sure whether I agree, but some people say that we of course have this tremendous increase of computational complexity. So what I can do with my phone today, a supercomputer was maybe able to do in the 70s or 80s. that's not just due, obviously, that's also due to more hardware power, but it's also due to much faster and much smarter algorithms, like this one. I will show you in a second that this one is actually running in Python, so that's Sage, and Mathematica as well. So both of them use this algorithm for their multiplication. And I'll show you in a second how to see that. But I hope that statement is, I hope it's also clear why that statement is absolutely fantastic. First of all, the idea is just great. It's divide and conquer. And you do it for polynomial multiplication, which is just super, super important. But actually, you can do it for multiplication. The only thing you need to do is you need to replace the action by some periodic extension of like binary, for example. Just think of this as the 2, the x to the k, and the 2 to the k, and you can run exactly the same multiplication algorithm for numbers. Right? So multiplication for numbers, as I was saying, in fact. And because you're a group of mathematicians, I was able to say polynomial multiplication is really important, but honestly, multiplication is just really important. And now we go down to 1.59. And it is just, this is absolutely perfect. I never thought I would end up using this, but I ended up using this idea, not the multiplication algorithm itself, but for a more complicated idea. And you can still do divide and conquer. You save one operator per step, and you can bring it down. In my case, it was from 2 to the n, the whole around 5 to the square root of n, which is still working, but it's much better. I also want to sell this idea of divide and conquer, which is just absolutely great. Okay. Okay, I did that so here's code that does that, and we can do that live. So let's do that live. So it will take me a second in Python. So Python, you can also run Python online, so you don't need to install anything. Again, I would like to highlight Python is Sage. So I would like to highlight that you can do everything yourself. Like it's not difficult. You should really do it. Let me just try to find my code here. Here we go. And again, if you're a beginner, it takes you an hour to do it. I did it in something like 10 minutes or so. Doesn't really matter. But it's this code. Very good. And we'll just do it. So it's whatever it does, you can see here, it calls itself. I define it. It has the obvious name, the person who discovered the multiplication. I want to multiply x and y. I do it base 10. So I just need to take a ceiling here to get my periodic 10 extension. You can do it in any base, and it will call itself. The whole point is it calls itself in the exactly 3 multiplications that we're seeing. That's the point. The program calls itself, which is the whole idea of divide and conquer. And I just multiply those 2 numbers, which are way too small for any demonstration. You'll see that in a second. And yeah, it will be very disappointing, but it's just because I'm stupid. Okay. It will tell me that I have 10.4. It took 10.4 milliseconds. Okay. So I was very happy because computers. You do it, the point is it calls itself. Right? Very nicely, and then I realized that the Python internal multiplication, which is the bottom one, naively, it's just way faster. So it's 9 nanoseconds instead of 10 milliseconds. And I got really disappointed with the result. And it's not because my numbers are not big enough, I will talk about that in a second, but it's just because Sage has it built in. So it immediately uses that anyway. And a real programmer is better than me, right? That's the whole point. So they can do much better. Anyway, so that's just me failing. But I would like to sell again the story that it's not difficult to actually do it yourself.
What does wall time mean?
And the total time. The total time is the wall time.
Like wall time is the thing that you see on the clock.
Yeah.
From starting the process, like literally the time on the wall. But other processes might interrupt them, so CPU time is the amount of time that actually spends.
Good. Let me go back to my slides if I can find them. So I did it. We just saw that live. It's a bit machine depending. So apparently I was doing much better today. So last time I got 18 nanoseconds and 10 milliseconds for the other one. But it's a bit machine depending. But you can still see that the bottom one, the next multiplication, is much faster. And the point is it has a goal. So and I can actually demonstrate that. I wasn't able to do that in Sage, but I can demonstrate that in Mathematica actually. That it has it built in, but let me just
Like it's I think it's important that people that don't know stuff know, like you can just, so something like Python or Sage or whatever is interpreted. And if you call a Python routine, it's calling something that's compiled.
yes.
And you can never compete with it.
You never do that. I was just like I was hoping what I was doing is weird because that's how I function. Fine. But I was kind of thinking that Python doesn't do it, just use plain numerical multiplication. Okay. And eventually this one could be actually fast. But you're absolutely right that it's not going.
Actually, another point, both Magma and Python underneath it all have the external routines encoded in C, C++. And so if you're calling a function, an intrinsic function from Magma, it will just go straight to the C code.
Yes.
So you don't have to forget of actually calling
That's
it.
right. Yeah, I know. I was just saying I was doing it. I just didn't. That's how I found it. See a problem, I put it in my own code, but it might not be all the way. Anyway, the algorithm itself is just fantastic, and there is a reason why all of these systems use it, right? So because it's
And are you sure? I mean, it's really surprising to me that Python doesn't use it. Like, right there. Are you sure that Python doesn't use it?
it does use it.
So you're writing interpreted code to do something and competing with compiling.
It's a very kind of
You know, you're gonna lose by that.
that's right. That's it.
But immediately.
That's right. It was a really bad idea, yes, exactly. But failure is part of life, so there you go. Really, again, promote the idea that it's actually not so difficult to do it yourself. In this case, it's kind of useless. You shouldn't, but it wouldn't be so difficult to do it yourself. Right, to come back to your question, n log n is the best one. So these algorithms have to be polished. So in the 60s, 70s, there was a huge kind of run on how to polish the algorithm itself. So I will compare them in a second with that. So it went down to log 5 over 3. Right here. Oh, yeah, you have to do it, right? Then log 5 over 3. Yeah, the one that stood for 40, 50 years, the straight out of stuff, it's just essentially n log n. It has a log n. It's n, log n, log n, log n, and log n is technically constant, so you can never ignore it. And then there was a recent breakthrough, and they showed, and in this beautiful paper that you can actually do an n log n based on the version of the fast Fourier transform, which I don't have time to do, but kind of fast Fourier transform is also divided transform, so another version of the transform. And to come back to your question, it's conjecture that this is the best you can do. Proving that it's the best is usually a bit tricky, but it's conjecture that this is possible. In some sense, there was a recent breakthrough, and we might have to optimally.
Is this like a practical change anything, or is?
Yeah,
That's
that's an excellent question. So all these algorithms compare is the worst case runtime. We should compare the average runtime, in particular for small numbers. But for example, Tubbenhauer started is around since 1970, and still both Mathematica and Python still use the one I showed you. So this one is more practical. also theoretically for really large functions. This was bad. So if you would need to multiply really large numbers, then you're going to calculate 20 digits of pi, and you're going to multiply very large numbers, then you probably will do this one. But it takes up thousands of digits before they make it.
The average runtime is slower, you're saying? Or
I'm not sure that anyone really did that formally, but in practice, average runtime works.
Yeah, I would disagree. I think that it's really important in these complexity things to be aware of, you're talking about complexity if n goes to infinity.
Yes.
And very often you have something that's reasonably simple to implement, like the algorithm you're discussing, whose complexity is low early and then picks off the very, very large numbers.
Yeah.
And then these more complicated algorithms typically start off much higher, and then they slowly sink down, and then they'll sink below at a scale that would never occur in a computer. You know, at a scale where you have like
I was wrong. Exactly.
billions and billions of digits in it.
It's like starting to high, just growing so slowly.
Yeah.
Very far out.
I take it back. I think in this case goes down where it's the average number of computer around the first getting with them anyway. The real point why they have used is that it really takes the money for really large numbers. Like all of these, and in my original picture, I had this analysis and then something like this. The n0 might be really large. Like you don't know what's going on with the beginning. And I have actually an illustration for you, which I can run now.
Another comment. So it's kind of interesting that this is a super beautiful story, and maybe I should mention David Harvey is going to study, and he's a great person to talk to. And also, so the Kolmogorov conjecture that this complexity is involved in swimming, and it's just been this like incredibly interesting development from this wrong conjecture of a great mathematician.
Okay, let me do it bigger. So this is essentially what Jody just said, and of course programmers are aware. So what I'm doing is running really large calculation to the I, and then take factorial, like I said, a lot of multiplication of a lot of large numbers. Okay, if you do that, so I is on the x-axis and the time is on the y-axis, you will see. And in this case, mathematica, you would actually swap at one point when the numbers get too big from plain multiplication to the other one, because the other one already has that problem that it's too slow for this one. It turns out that for my machine, the swapping point is not optimal, as you can see, that's why we have to do that. But that's really dependent. Yeah, so that's what all good algorithms should do. They should roughly analyze the size of the numbers and run the appropriate algorithm. I think this optimal algorithm is optimal for very large numbers. I think the n0 will be very large.
Actually, in this case, is that just because the small numbers less than 2 to the 10 is the actual multiplication carried out on the chip, not in the software, not in part of the software. So seeing that.
Right.
Maybe just based on what John's saying, it's like really important to remember that computing is kind of like a whole lot of totals. And you think that there's only 3 totals, but actually there's 17. And you know, like multiplication might be happening on the chip, it might be like some very low level implementation on top of what's happening on the chip, and it's fixed. Like the more you get into the total, the more totals is allowed up there.
So there's a huge difference between kind of abstract and
The expression of totals, you know, this like what the world, you know, there's all stories about the world, like the world lives on top of the planet. What's that support? It's the total. But what's supporting the total? Oh, it's another total.
What I'm trying to say,
What are the chips? It's the one total. And then there's you.
maybe it's out for so So there's all these abstract analysis, they kind of there's another experimental analysis department that comes into that. And of course, people working in this area have done that already. So I'm kind of slightly cheating here. Oop. All right, let me just finish with a comparison picture, and then I finish a bit early. Yeah, so here's my log plot again. So not try for small numbers, but I just put it through by myself. So certainly don't do that by hand. So n squared is the grid one. And we have those various, let's go back, the various ones here. So log 5 over 3, and then there's this log n, which is essentially a constant, and then the final one here appeared 4 years ago or something.
And log n is equals to n.
Yeah, exactly. Note here also, maybe I can get that if you zoom in, maybe you can just see it. The red one is the n log n. What is it? N log n. And the green one is the n log 5 over 3. And even in the abstract analysis, it takes a while for the red one to be faster than the green. So even in this abstract picture, they're a little bit difficult to compare. But of course, in the limit, the n log n log n is kind of the second best. Let me just finish by some. So this computation with numbers is absolutely great, but divide and conquer is just everywhere in this field, and it's just extremely great. I will run some animations for you in a second. The most important one in some sense, or at least the oldest one I found, is Euclidean algorithm, which is a form of divide and conquer. Because what you do is you get a divide, right? So whatever, 2 and prime plus r or something. And then you just call it again, right? And call it again, the numbers call it again, because the numbers call it again. And it's really good. This one is really great. It runs quite fast in at least in this complexity. It's a log. Again, I'm dividing A and B, then dividing A and B. And it will be something like the max term of the mid. So it's essentially even the size. Okay, pretty good. Then they have binding insert, which we'll see in a second live. I'll have an animation for you, which according to formally it appears in the paper in the 40s, but who was it? Apparently the polynomials are new, but let me just run it for you. I have it here. If I can find it, it's kind of self-explanatory. Binary search. I want to find number 9. So what can I do? I can use linear, or I can do much faster, much smarter. I can divide my problem. And I think, oh, 5 is not 9, so 5 is smaller than 9. I throw it out and divide my problem. And divide my problem, I divide my problem. So this is really a great illustration of dividing a whole problem. Right? That's dividing your problem. Hope that's reasonably clear. Again, here, divide and conquer, run the n of n, for a log n. And let's just do the comparison to the log n. That's binary search. Then you also do it this way, it's probably 9 now, 5, 6, 7, 8, 9, 10. We can also do linear search, which is just the following. Oh, this is not 9, okay. 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 And so on. So just linear equation. And that's I hope that's kind of clear. Equal of n, because in the worst case, I will find 9. This is really simple idea of just dividing. Again, log n will be much faster. Do I have them in comparison? I do. Okay, let's wait for a second. I do have to compare. And it's famous fast Fourier transform, which some people call the most important algorithm. So for log n, it's again some version of divided conquer. And then we have merge sort, which I can run for you as well. Which obviously is again, which as you'll see, it will be divided conquer again. Oh gosh, come on. This is a bit better resolution, but you will get the point. So you want to order the set, and what you do recursively, you just split it, and you order everything. This small one, perfect. You order this one. You order the next one. You order the next one. The next one is already ordered. Of course, that could happen. And then you just run recursively for the next pair. So it's one step bigger. So you order those and so on. Very good. There we go. Let's just run it to the end. It just will take a few seconds. And then there will be the final order of the set, which is again much smarter than just kind of trying to order it in another way. So it's really divide and conquer again. Divide. This is a bit nicer because I had the power of 2, so there was an even division. But in the previous animation, you saw that you don't need it, but you don't really need an order of 2, the power of 2 to make it. So comparison again. Okay, I stop now. The binary search extremely fast compared to linear search. So which is also called one by one search. And end of n is a bit slower. It's kind of a strange comparison. You can only really compare green and blue because they kind of try to do the same, but just to get you a feeling what those complexities. Okay, I stop here.